He knows a lot about the science stuff, Professor Dave explains.
In the previous tutorial, we set up the problem of the quantum barrier potential. We defined 3 regions and used the boundary conditions to solve the Schrödinger equation for the system. This left us with a set of 4 equations containing 5 variables. Now we are going to use these results to examine the strange quantum phenomena we also described in the previous tutorial, and in particular that which is referred to as quantum tunneling. As we recall, unlike a classical particle, if a quantum particle is approaching this barrier with an energy that is less than the barrier height, there is still some non-zero probability that it will be transmitted through the barrier. In order to quantify the probability of this occurring, we need to define something called a transmissibility factor. This is defined as the ratio between the probability of finding a particle traveling to the right in region C, meaning it has traversed the barrier, and the probability of finding a particle traveling towards the barrier in region A. This won't be too difficult actually, so let's recall what the wave functions look like in regions A and C. Now, to simplify a bit, we can also recall that we have defined a wave traveling to the right as being equal to e to the ikx, and a wave traveling to the left as e to the negative ikx. So we can actually rewrite these wave functions as follows, where psi a of x equals psi a right plus psi a left, and psi c of x equals psi c right. Now let's do a trick. Let's define the probability of finding a particle traveling to the right in region A as psi star times psi, which is simply the probability density function for psi a right. As we know from previous tutorials, psi star is the complex conjugate of psi, which means that the complex exponential will be opposite in sign. When these two terms multiply, their exponents add together and will therefore cancel out to give 0, which gives us 1 for these terms, and leaves us with a star times a. Then we can define the probability of finding a particle moving to the left in region A precisely the same way, just with psi a left instead of right. Everything simplifies precisely the same way to leave us with b star times b. And finally, we can define the probability of finding a particle traveling to the right in region C this way as well, and again we are left with c star times c. To reiterate, we want to define these probabilities, moving left in A and moving right in C, with respect to the probability of the particle moving to the right in region A, which we can call the incident particle. This will allow us to define reflection and transmission coefficients, where a particle moving to the left in region A has necessarily been reflected by the barrier, and a particle moving to the right in region C has necessarily undergone transmission through the barrier. So as we just stated, we need to find the ratio between the probability of finding the particle traveling to the right in region C versus traveling to the right in region A, and we have defined those by determining the respective probability density functions. So we can take the relevant results and place one over the other to get c star times c over a star times a. We can define this as a transmission coefficient t. To make things easier, we can introduce a lowercase t and set it equal to c over a, so that this expression can be abbreviated as lowercase t star times t. So what does this term represent? Well, again, this coefficient gives us a mathematical description for what we described earlier, the probability of finding a particle traveling away from the barrier in region C versus traveling towards the barrier in region A, which gives us information about the probability that quantum tunneling will occur. We can also define a similar reflection coefficient, defined as b star times b over a star times a. Again, we can define lowercase r as b over a, allowing us to abbreviate this expression as lowercase r star times r. This tells us the ratio between the probability of finding the particle traveling to the left in region A and traveling to the right in region A, which gives us information about the probability of the particle being reflected by the barrier. So when considered together, these two parameters, the transmission coefficient and the reflection coefficient, describe the likelihood of the quantum particle either passing through the barrier or being reflected by the barrier. If the energy of the particle is significantly lower than the height of the barrier, or V0, then we should expect a rather large reflectivity factor and a rather small transmissibility factor, since even in the quantum realm, a barrier is still a barrier. Let's now get quantitative by calculating the transmission factor T for this system. So let's take our system of four equations we derived in the previous tutorial, and since T describes the ratio of C and A, let's divide all of these equations by A so that we can get T. For the first equation, A over A is 1. B over A can be represented by R as we just introduced. And then to keep things simple, let's represent F over A as lowercase f and G over A as lowercase g. We can do the same thing for the other three equations, using our new lowercase variables, and whenever we have C over A, we place a lowercase t. This will be what we want to isolate, since this will give us our transmission factor. To do this, we will have to perform some manipulations on this system of equations that are similar to what we learned when studying linear algebra. First, we will multiply the third equation by k below, so that will be a coefficient for each term now. Having done this, we are now able to add the third and fourth equations together. As you can see, the second term in each, with the lowercase g, are opposite in sign and will cancel out. The first term in each is identical, so that stays the same, and we simply put the number 2 out front. And then the terms on the right side of each equation will add together to give us a sum. Next, let's isolate lowercase f in the fourth equation. This entails dividing both sides by 2k below times e to the k below times a. This can then be simplified, since both terms in the numerator have t and the same complex exponential, so let's factor those out. And we can actually simplify a bit more by bringing the real exponential from the denominator up to the numerator, which we can do if we invert the sign on the exponential term. Then we will simply subtract k below a from I k naught a and factor a out of the difference, which will leave us with this. So there we have an expression for lowercase f, which again is equal to uppercase f over a. Next, we want to get lowercase g. Let's go back to our original set of equations before we began manipulating to get f. Let's again multiply equation 3 by k below. Now this time we will subtract equation 3 from equation 4. That means that this time the first term will cancel out. We get negative 2 times the second term, and the relevant difference on the other side. Simplifying precisely as we did a moment ago to find f, we can arrive at this expression for lowercase g. And now finally, we need to isolate lowercase t. Let's start at the beginning once again, and this time the first thing we will do is multiply the first equation by I k naught. We will now add this to the second equation. The first term in each is I k naught, so we get 2 of those. The second terms are the same, but of opposite sign, so they cancel. And on the other side, we add together and factor out f and g to get this. Now recall that we just solved for f and g, so let's actually plug those in here, which will give us something that looks a little messy at first, but we can handle it. To simplify, we can do a few things. First, notice that for each term, we have the same parenthetical twice in succession, so let's just combine them by squaring. Also, since t is present in both terms, let's just factor that out to get this lengthy term in brackets times t. We can also change this from a sum to a difference by pulling the negative sign in this denominator to the front of the term, which leaves us with the same denominator for the two terms. That means we can also pull out the denominator since that's present in each term, and then the common portion of the complex exponential as well. That will leave us with this. Next, we are going to expand those squared parentheticals, simply by foiling them just like we learned in algebra class. Looking at the first of these, for I k0 quantity squared, since I squared is -1, we get negative k0 squared. Then, squaring the second term, we get k below squared. And then we get I k0 k below twice, so we put a 2 there. And for the other one, everything is the same, except the negative sign on k below means we have -2 for the last term instead of +2. Now, to go further, we will need to recall the definitions of hyperbolic sine and cosine, which we discussed over in the mathematics series. In that tutorial, we saw that these functions could be defined by the following expressions. Hyperbolic cosine of x equals e to the x plus e to the negative x over 2. And hyperbolic sine of x is the same thing but with a difference instead of a sum. Now, how can we use these definitions to simplify our equation? First, let's continue to rearrange what we have. Notice that we have two expressions that are repeated. First, this one with 2 terms, which is the same in each parenthetical, and then this other term, which is the same but opposite in sign. We can rearrange by distributing the e terms such that they multiply each of these two expressions, though this time we can also distribute this minus sign so that this last term is now positive. Now we can regroup according to these two terms, factoring them out such that each resulting term involves a binomial with the two e terms, one of which is a difference and the other of which is a sum. Now this is where we get clever. We can replace these exponential terms with hyperbolic sine and cosine. But since the expressions are normally over 2, and here they aren't, we have twice the regular expression. So let's put 2 hyperbolic sine k below a and 2 hyperbolic cosine k below a. We also have to put a negative sign in front of the first term, as this expression follows the general form e to the negative x minus e to the x, rather than the other way around, so we have to compensate by factoring a negative sign out of that term. For the second term, it is irrelevant because sums are commutative. Now we can finally solve for t. Let's do this by dividing both sides by this enormous term. Then we can multiply both sides by this denominator, 2k below. And then we can divide both sides by e to the ik0, which is the same as putting e to the negative ik0 in the numerator on the other side. Also, let's just distribute this negative sign across this binomial, thereby flipping the sign of the terms. So we are almost done, but we must realize that what we have here is lowercase t. The transmission factor we are looking for, represented by uppercase T, is defined as t star times t. This means we are going to have to multiply this entire expression by its complex conjugate. So first, let's write out the conjugate. This will simply involve flipping the sign for any term with I in it, and this will be multiplied by the original expression. Now we can make our lives a little easier by abbreviating some of this with constants. Let's define gamma as being equal to k0 squared minus k below squared. And let's define kappa as 2k0 k below. In the denominator, we have a product that takes the form a minus ib times a plus ib. We know that this gives us a squared plus b squared, so we can just square this first term, which gives us 4 gamma squared hyperbolic sine squared k below a. And then we add to that the square of the second term without the I in it, or 4 kappa squared hyperbolic cosine squared k below a. In the numerator, the two i's multiply to give -1, which cancels out the negative sign out front, and the exponents on the e terms add together to give 0, which gives us 1 for those terms. This leaves us with 4 kappa squared. Now let's divide through by 4 and get rid of them, and then we can use another trick, and that is the identity which tells us that hyperbolic cosine squared x minus hyperbolic sine squared x equals 1. We can use this to change the hyperbolic cosine squared term into 1 plus hyperbolic sine squared. Let's distribute kappa squared across here, and then we can factor out the hyperbolic sine squared term from these two terms to get the quantity gamma squared plus kappa squared times hyperbolic sine squared k below a plus kappa squared. Let's now divide through by kappa squared, giving us 1 in the numerator and this in the denominator. Now, given where we are at in solving for t, we are ready to plug back in our original expressions for all of these constants. This means the expressions we just defined as being equal to gamma and kappa, but also the definitions of k below and k naught, which we outlined in the previous tutorial. To keep things as simple as possible, let's do this one chunk at a time. First, let's find gamma squared over kappa squared plus 1. Let's plug in the expressions. So we have the square of a binomial up top, and that gives us each k term to the fourth minus twice their product. In the denominator, we just square it, and to this fraction, we add 1. In order to do the addition, let's get a common denominator, so we change 1 into this expression over itself. Adding the numerators, -2 of these plus 4 of these gives us 2 of these, and we are left with this. We can now split this back up into 3 fractions, each of which will involve canceling some terms. 2 of the k naughts for the first, 2 of the k belows for the second, and both of the k terms for the third, as well as cutting the numbers in half. Now let's plug in our definitions for these k terms. For this first fraction, we plug in the squares of the expressions, and we cancel out the h bar squareds and the 2m, leaving us with e over 4 times the quantity v naught minus e. For the second term, we get v naught minus e over 4e. And then 1/2 stays as it is. To get a common denominator, we can multiply the first term by e over e, the second term by v naught minus e over v naught minus e, and the third term by both of these. That gives us our common denominator, and the numerator becomes e squared plus v naught minus e quantity squared plus 2e times the quantity v naught minus e. Let's recognize that this is actually a perfect square, which we can express as the square of the binomial e plus the quantity v naught minus e. But within the parenthetical, the e terms actually cancel out, which leaves us with simply v naught squared. So this can be plugged in where gamma squared over kappa squared plus 1 used to be, which leaves us with this. And now we are finally approaching something that we can try to understand conceptually, such that we can discuss a particle with some energy E with respect to the height of the barrier. To make this a little more readable, let's define another factor, eta, which represents the energy of the particle with respect to the barrier height. This will allow us to derive the final form of the equation for the transmission factor, and since we've already had more than enough algebra, let's just skip right to it. That will look like this. From this, we can also quickly derive the reflectivity coefficient. We know that the particle will either be transmitted or reflected. There are no other possibilities, so t plus r must equal 1. Therefore, to get r, we simply subtract t from 1. And now we have expressions for both of these parameters. Whenever we study a particle with energy smaller than v naught, we will plot t and r for the case where eta is less than 1. If studying a particle with energy greater than v naught, we would plot t and r for the case where eta is greater than 1. Let's now wrap things up by applying this information. Imagine an electron traveling towards a region where it finds a certain barrier. This could be something like an imperfection on a wire where the electron is traveling. Say the electron approaches with energy E, and the barrier height is 10 to the -6 electron volts. If you are not familiar with this unit, an electron volt represents the amount of energy an electron gains when it encounters a 1 volt potential difference. In the world of a tiny electron, 1 electron volt is quite a lot, so a micro electron volt, or a millionth of an electron volt, is a more reasonable potential barrier. Just a moment ago, we found the coefficients r and t, which tell us the reflection and transmission probabilities for a quantum particle that encounters a barrier. So we will use these to construct some graphs which apply to an electron that encounters such a barrier. Now, in our equation, we need to find all the parameters within k below, since we have normalized the energy in the unitless quantity eta. This is as such simply because both V and E have the same units of energy, so if we divide them as we do with eta, we are left without units. So our expression for k below is as follows, and we need to get this in terms of eta, so we can factor V0 out of this parenthetical to get 1 minus E over V0, which is 1 minus eta. Now some of these are constants which are known. The mass of the electron and the value of h bar, both in electron volt units, are as follows. Now with these parameters, we can plot both t and r as functions of eta. For some dimensional reference, we regard the electron radius as being about 10 to the negative 15 meters. So let's identify the barrier size that is traversable by an electron. The length of the barrier is given by the parameter a. Let's say we are looking at a barrier with a length of 1 nanometer. This is something that is realistic in the realm of nanotechnology, so we are essentially examining whether quantum tunneling is a phenomenon that will be relevant for those who work on this type of circuitry. Let's use the results we just got for T and R. If an electron encounters this 1 nanometer length barrier, we get this plot. What we are looking at here is the equations for T and R as eta changes. Because the barrier height is fixed, we are varying the particle's energy to see how this impacts the transmission and reflection coefficients. So again, the red curve represents the transmission coefficient, and the blue curve represents the reflection coefficient, both in terms of eta, which is the ratio of the particle's energy and the barrier's height. When eta equals 0, the particle's energy is 0, so there is no chance that transmission through the barrier will occur. This is why when eta is 0, t is 0 and r is 1. Then as eta approaches 1, meaning that the particle's energy approaches V0, a tiny chance of transmission through the barrier begins to develop. That's why the red curve dips up at the end. This is an example of quantum tunneling. So even with a barrier that has a length of 1 nanometer, which is unbelievably long to an electron, it can still potentially traverse the barrier if it has sufficient energy. Now let's use a smaller barrier length, perhaps 1/10 of a nanometer. Now the chance of the particle being transmitted will increase because the penetration depth comes closer to the length of the barrier at lower energies. We can see that here, when the particle has an energy that's just slightly lower than the barrier height, there is already a probability of more than 50% that it will be transmitted. So we can see that transmission of a quantum particle through a barrier is possible even when the particle has an energy that is lower than the barrier height. Again, this is called quantum tunneling, but we must also consider the equally bizarre scenario where a particle with an energy that is greater than the height of the barrier may still be reflected by the barrier. Let's recall our system of equations that describes this scenario, which no longer have real exponential functions, since the particle propagates freely in all regions. Working with k above now instead of k below, and omitting all the algebra since the process is nearly identical to what we already went over, the solution will have a regular sine function instead of a hyperbolic sine, and it will look like this. We can rewrite k above as follows. We can then plot this just as we did before. Let's start with the 1 nanometer long 1 microelectron volt barrier. Let's plot T and R for values of eta from 1 to 2, meaning that the particle would have an energy equal to V0 when eta equals 1, and twice V0 when eta equals 2. Remember, before we said that the chances of transmission when eta equals 1, when the particle came from below the barrier, were slim, so we should find the same for a particle coming from above the barrier as well. And in fact, that is what we see. T is almost 0 at first. Then things get more complicated, where as energy increases, the particle has a much greater chance of being transmitted. Then it dips down again, then back up, and so forth. At first, this does seem like a rather strange result, with many oscillations, rather than the monotonic behavior or continuous and gradual change of the previous situation. This is due to the discrepancy in hyperbolic sine and regular sine functions, as only the latter demonstrates this sort of sinusoidal behavior. This oscillation comes as a result of our boundary conditions. The wave function will only be able to traverse the barrier if its shape at the boundary matches the shape of the wave functions that are allowed on the other side, so to speak. Due to the specific constraints of this problem, this set of parameters yields this specific oscillation. What this also means is that, somewhat surprisingly, there is a relatively high probability of reflection at very particular energies, even at specific instances where the energy of the particle is significantly higher than the barrier height. This is a result that should be just as intriguing as quantum tunneling. Lastly, let's see what happens if the barrier length is much shorter, like say 20 times shorter. Now we can see that the probability of transmission is very high, almost 100%, once the energy becomes significantly larger than the barrier height. But we do still see a reasonable probability of reflection when the particle's energy is close to the barrier height. The behavior of the system is becoming closer to a more classical situation, like throwing a ball over a fence. If the fence is low, it's very easy to toss the ball over to the other side. So, over the past 2 tutorials, we have tackled our second quantum problem. This is the scenario in which a quantum particle encounters a barrier potential of some height. By using this model, we derived a set of equations which describe both quantum tunneling and quantum reflection. As it turns out, these two effects are indeed quite important in understanding modern technology, from the principles that dictate how transistors operate to the complicated physics of scanning tunneling microscopes. So it is clear that even something as abstract as quantum mechanics was eventually found to have technological applications. Let's now move forward and check out yet another type of quantum problem. Thanks for watching. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.